Welcome back to the second module in the 9th week of getting started with competitive programming. So in the previous module, we just saw about the deep relationship between the value of a maximum flow in a flow network and the capacity of a minimum cut in the same network. In this short follow-up module, I want to talk about a problem that will give us an opportunity to implement the minimum cut algorithm that we hinted to last time. So this one is called police chase. It's a problem that you can find in the graphs section of CSES. If this is the first time you're solving a problem on the CSES platform, you will need to set up an account, but that's very quick and easy to do. So there is, as always, a link to the problem in the description of this video. So I hope that you can check it out and follow along. So here is the problem statement. Kaleppi, I hope I'm pronouncing that right. Kaleppi has just robbed a bank and is now heading to the harbor. However, the police wants to stop him by closing some of the streets of the city. What's the minimum number of streets that should be closed so that there is no route between the bank and the harbor? So I'm going to assume that our friend is just finished robbing the bank and is at the source vertex, which corresponds to the bank here. And the police want to shut off some of the roads so that no matter what our friend does, he's not going to be able to reach the harbor. So you can probably already see where this is going. You want to model the streets in the city as some sort of a flow network, and you want to think of the bank as the source and the harbor as the target, and of course your goal of closing off the smallest number of streets so as to cut off all the connections from the bank to the harbor is going to correspond to a minimum cut in this flow network. Let's take a look at the example that's given as the sample input in the problem statement. So we have 4 locations. The bank is always a location with index 1, and the harbor is always the location which has index n, which is the number of vertices. In this case, n is 4. So the source and the target are shown as the green and the red vertices here. The remaining edges are as shown. And if you like, you can pause here for a moment to think about what would be the best solution in terms of what would be the smallest number of roads that you can remove to disconnect the bank from the harbor. Alright, if you stare at this for a minute, you can probably conclude that it's not enough to remove just one edge. You could try each edge in turn, for instance, and realize that you're going to need at least 2 edges to disconnect the source from the target in this example, and it turns out that 2 edges are in fact enough. So for example, you could try to delete these 2 edges here, and you'll see that once you do that, you disconnect the harbor from the bank. So pretty much just by definition, what you're looking for is a minimum cut between vertex 1 and vertex n. And as I said before, this is something that we are very well equipped to do by now because we already have an implementation of the Ford-Fulkerson algorithm. So the idea is to find a maximum flow and then look at the residual graph that you obtain at the end of this process and look at all the vertices that are reachable from the source, and that is going to be your minimum cut. And what you want to actually return is the edges that cross this cut. So let's take a look at how we are going to do this in the implementation. So here is what we are going to do after we have finished reading in the graph and running the MaxFlow algorithm on it. So the process of reading the graph in and running MaxFlow on it is completely straightforward. The input is given in a very convenient way, so you just have to keep reading the edges and adding them to your MaxFlow object, and you can simply invoke the Edmonds-Karp function after you have built up the graph. So I'm not showing you that part of the code, but in case you'd like to take a look, you can find it in the usual place in the official repository, and there is a link in the description as always. So after all this is done, what we want to do is find the set of vertices that are reachable from the source vertex, which in this case is the vertex labeled 1. So we are going to do this using a helper function called reachableset, and I'm going to talk about how reachableset is implemented in just a moment. But again, if this is something that you want to try and do on your own, it is a very good exercise. All you have to do is copy paste the BFS implementation and just introduce a variable that can keep track of all the vertices that you encounter in the process of running the BFS from the source vertex. So feel free to try that out on your own. This would be a good point to pause the video and play around with your own implementation, and you could come back and exchange notes. Alright, so let's say that we have some implementation of reachable set. As I said, we're going to get to that next. But let's suppose that we store in the variable scomp the set of all vertices that are reachable from the source. Now, the next thing that we do is run a little loop that goes through all the vertices and figures out which are the ones that don't belong to scomp. This will be the set T. The reason we want to build out T explicitly is because it's just going to help us identify all the edges that cross the cut, which is in fact the solution that we are interested in. Notice that in the police chase problem, you're actually asked to output a set of edges corresponding to streets that the police can block off. So if you just had to output the number of streets that need to be blocked off, you don't really need to do any of this. You can simply return the value of the max flow and you would be done. However, in this problem and in many problems of this kind, you're often asked to explicitly output some valid solution. And fortunately, as we have discussed, the Ford-Fulkerson algorithm automatically gives us access to a minimum cut, and all that remains to be done is to basically identify all the edges that are crossing this cut. Now, of course, to do this, you don't have to explicitly identify the set T like I'm doing here. You could instead simply loop over all the vertices in S, look at the edges that are incident on these vertices, and identify all those edges that have their other endpoints essentially not being in S. And that's an alternate way to discover all the edges that are crossing the cut. I just found this more convenient to just interpret visually, so that's why I'm doing it this way. So the first for loop here essentially identifies all of those vertices that don't belong to scomp, which is the part of the graph that's reachable from S in the last residual graph from Ford-Fulkerson, and this essentially constitutes our set T, which we are calling T-comp here. Finally, what we do is run a nested pair of for loops, which essentially goes through all pairs of vertices such that one of them is in S and the other is in T. And I've written a small helper function that just tells me whether a pair of vertices is an edge or not. So if I comma j is an edge and I is in S and j is in T, then I'm going to add this to my cut. In this case, I'm just printing it out directly, but you could also store it in a solution in case you need to use the cut for something else going forward. For this problem, it's just enough to print this list of edges and you are done. Now let's just take a quick look at how reachable set works. So this should look very familiar because it's essentially the BFS subroutine, but I've decluttered it a bit so that I don't have to keep track of parent information because that's not so relevant here. But instead we've introduced an answer variable, which essentially is going to just keep track of all the vertices that we meet as we do this BFS. So every time we see a new vertex, just after we push it back on the queue, we also add it to the answer vector and we just return answer. That's the set of all the vertices that are reachable from S. By the way, if you're just following along on the video and writing your code as we discuss, then notice that there are parts of this function that are missing. So in particular, all of the initialization is missing, and you will need to declare the variables. Make sure that the queue has the vertex S to begin with and that the distance vector has been initialized appropriately and that the distance of the source vertex is set to 0. So these are a few things that you don't see on the slide, but you can once again find the complete code in a link that is there in the description. So you can refer to that instead if you're looking for fully workable code, but ideally you're just trying to write this out yourself as well, just for good practice. However you choose to do it, I hope that you end up with a working implementation that makes you feel confident about tackling problems that are based on min-cut going forward. In the last module for this week, which is coming up next, we will look at a slightly more sophisticated application of min-cut, and while we are at it, we are going to learn about another fundamental and truly beautiful duality theorem in graph theory. So I can't wait to tell you about that, so I'll see you in the next module. Thanks for watching.